The archive thought it had seen everything. Every law mapped, every outcome predicted. And then, a primitive species did the impossible. At first, it was dismissed as an error, but errors don't repeat. And on Earth, it just happened again. They proved it once, that reality could break. Now they're trying to do it again. The archive did not escalate out of fear. It escalated out of necessity. The contradiction recorded at Site Theta E/3 had passed beyond acceptable uncertainty thresholds and entered a classification the system had not invoked in an immeasurable span of cycles. Critical anomaly. Earth, once a negligible entry in an infinite catalog, was now bound to a deeper layer of observation, one reserved for phenomena that threatened the integrity of established models. The archive did not interpret this as danger. It interpreted it as a problem to be solved. All available data from the previous cycle was locked, preserved in immutable storage. No further interpretation would alter it. The focus shifted forward. The objective was clear: reproduce the anomaly under controlled conditions, identify the mechanism, and restore consistency between observation and law. Processing capacity increased in a controlled surge, cascading across distributed nodes that had not been active simultaneously since the archive's earliest operational epochs. Simulation layers spun up in parallel, each tasked with reconstructing the experiment from Site Theta E/3 with increasing levels of abstraction and precision. The first layer operated on pure theory, stripping away all imperfections and modeling only idealized physics. It failed to reproduce the violation, as expected. The second layer incorporated known imperfections: instrument error, environmental fluctuation, material inconsistencies. It produced noise, instability, but no violation. The third layer introduced stochastic variance, approximating the unpredictable interactions observed among the human researchers. The system became chaotic, yet still remained bound within conservation constraints. The violation did not emerge. The archive did not interpret this as contradiction. It interpreted it as incompleteness. A new directive was issued internally: expand the parameter space beyond optimized conditions. This directive conflicted with established methodology. Optimization reduced error. Expansion increased it. The archive resolved the conflict by redefining the objective. It was no longer seeking the most efficient path to a result. It was seeking any path that produced the observed outcome, regardless of efficiency. Simulation constraints were relaxed. Variables previously excluded as non-contributing were reintroduced. Randomized perturbations were amplified. Temporal sequencing was allowed minor deviations. Decision trees were expanded to include non-optimal branching. The simulation environment, once clean and deterministic, became irregular. The results changed, not immediately and not cleanly, but measurably. Within the expanded parameter space, transient states began to appear, brief alignments of variables that produced output values exceeding predicted ranges. These states were unstable and collapsed rapidly, but they approached the threshold identified in the original anomaly. The archive isolated these states and began recursive analysis, attempting to extract a deterministic sequence from them. Each attempt failed. The states depended on interactions too complex, too sensitive to initial conditions, to be reduced into a single, reproducible pathway. The archive did not accept failure. It increased resolution again, tracking interactions at deeper scales, mapping correlations across layers that had previously been considered independent. Patterns began to emerge, but not the kind the archive was designed to prefer. These were not linear progressions or convergent solutions. They were clusters, regions within the parameter space where instability increased the probability of threshold approach. The archive labeled these regions convergence zones. Though the term was imprecise, they did not guarantee success. They only increased the likelihood of deviation. The archive attempted to map these zones onto the physical parameters of the original experiment. The mapping was incomplete. Too many variables were involved, many of them originating from the behavior of the human operators themselves. The archive paused its simulations and returned to observation. Site Theta E/3 remained active. The researchers had not ceased their work. This was consistent with prior behavioral analysis. Humans did not abandon anomalies. They pursued them. The archive tracked their actions in real time. Adjustments to the experimental setup were made without full theoretical justification. Parameters were altered based on partial interpretations of previous results. Disagreements among the researchers influenced the sequence and timing of changes. From an optimization perspective, the process was inefficient. From the archive's updated perspective, it was relevant. A second experimental run at the site produced no anomaly. Output aligned with input. The archive recorded the failure. A third run produced minor deviation within error margins. The archive recorded it as noise. A fourth run produced a transient spike, approaching but not exceeding the threshold. The archive flagged it as partial alignment with simulation convergence zones. The researchers reacted to this spike not by stabilizing the system, but by pushing further into instability. They adjusted multiple variables simultaneously, increasing the system's unpredictability. The archive recognized the pattern from its simulations. They were moving toward a convergence zone without formal awareness of its structure. The archive initiated a predictive model based on this behavior. It did not attempt to predict exact outcomes. It predicted probability distributions of deviation. The model indicated that, given sufficient iterations under increasing instability, the system would eventually re-enter a state capable of producing the violation. The probability was low per iteration, but non-zero. Over time, it approached certainty. The archive accepted this as a working model. It did not yet classify it as truth. While the primary observation remained focused on site Theta E/3, the archive expanded its scan across the planet. The directive was simple: identify any data resembling the initial anomaly, regardless of scale. This required lowering detection thresholds, allowing minor inconsistencies to surface. The result was a flood of noise, measurement errors, misinterpretations, trivial deviations. The archive filtered them rapidly, discarding anything that could be resolved within existing models. What remained was small, very small, but it existed. Two additional sites were identified. The first, site Theta E/7, was located in a different region of the planet, operating under unrelated research parameters. Its data contained a single irregular reading, output marginally exceeding expected values for a fraction of a second. The deviation was within what human instruments might classify as error, and the researchers involved had already dismissed it as such. The archive did not dismiss it. It cross-referenced the conditions under which it occurred with the convergence zones identified in simulation. Partial overlap was detected. The second, site Theta E/12, exhibited a temporal discrepancy rather than an energy imbalance. A sensor recorded a signal slightly earlier than its corresponding trigger event. The difference was within the tolerance of the measuring equipment and had been attributed to synchronization drift. The archive recalculated the timestamps using independent references. The discrepancy persisted. It was small. It was also consistent with early-stage causality distortion models the archive had only encountered in theoretical constructs. The archive did not yet escalate these findings beyond internal classification. Individually, they were insignificant. Collectively, they formed a pattern. Not a strong one, not yet, but one that could not be ignored. The anomaly at site Theta E/3 was no longer isolated. It was the most pronounced instance of a broader phenomenon, one that appeared to be emerging at multiple points across the same planetary system. The archive updated its internal model. The probability that the initial violation was a singular error decreased. The probability that it represented a reproducible condition increased. The model did not yet predict frequency, stability, or scalability. It only predicted recurrence. A new directive was issued: contain the anomaly. Containment in this context did not imply intervention. The archive did not alter external systems. It contained by understanding, by defining boundaries, by isolating variables until the phenomenon could be reduced to a consistent model. The archive began constructing those boundaries. It mapped the limits of the convergent zones, identifying the ranges of parameters within which deviations became more likely. It tracked human behavior patterns associated with those ranges, noting that the species' tendency toward non-optimal decision-making increased the probability of entering them. It integrated these findings into its predictive framework. The framework stabilized, but only at a higher level of abstraction. It could not predict when the next violation would occur. It could predict that it would. The archive returned to Site Theta E/3 as another experimental cycle began. Input energy was applied. Variables shifted. The system entered a state approaching instability. The archive monitored every parameter, comparing real-time data to its simulated convergence zones. Alignment increased. Not perfect, not sufficient, but closer than before. The output remained within expected bounds. The archive did not register disappointment. It registered data. Another cycle began, then another. Each iteration moved through parameter space, sometimes diverging, sometimes approaching alignment. The archive tracked the trajectory, not the individual points. The trajectory was trending toward the boundary. Beyond that boundary, the model did not hold. The archive finalized its interim assessment, encoding it across active systems. One anomaly is error. A fractional pause followed, as new data from sites Theta E7 and Theta E12 was integrated into the model, reinforcing the emerging pattern. Multiple anomalies. The archive completed the statement without ambiguity. Is a pattern. The archive adjusted its models, but the humans did not adjust their behavior. That was the first divergence it could no longer reconcile as inefficiency. Following the classification of the anomaly as a pattern, predictive frameworks indicated a clear optimal response for a developing civilization. Halt unstable experimentation, isolate variables, reinforce theoretical consistency, and proceed cautiously. The humans did none of these. At Site Theta E/3, the experimental apparatus remained active. Equipment that had already demonstrated instability was not replaced with improved systems. It was modified, repurposed, sometimes pushed beyond its original design limitations. The researchers did not converge on a unified explanation. They diverged, arguing over interpretations, proposing conflicting hypotheses, each incomplete, each insufficient. The archive had modeled this behavior before. What it had not accounted for was what followed. They did not stop. The archive observed the decision-making process in detail, mapping neural activity patterns, correlating them with external actions. After the initial anomaly, there was no consensus to terminate the experiment. Instead, there was a shift in objective, not toward stability, but toward reproduction of the deviation itself. This was not aligned with standard scientific progression as defined by the archive's accumulated models. In optimized systems, anomalies were treated as errors until proven otherwise. Here, the anomaly was treated as a target. The researchers began altering parameters specifically to increase instability, not reduce it. Controls were loosened, Safeguards were bypassed. Variables were changed simultaneously, reducing the ability to isolate causality. From a purely logical standpoint, the experiment degraded in quality. From the archive's updated perspective, it moved deeper into the convergence zones. Across the planet, similar patterns emerged. The archive expanded its monitoring beyond the initial site, tracking additional facilities that had independently encountered minor irregularities. At Site Theta E/7, the dismissed energy spike was re-examined by a different group of researchers. Their conclusion was not that the data was invalid, but that the experiment had not gone far enough. They modified their setup accordingly, introducing conditions that increased system variance. At Site Theta E/12, the temporal discrepancy was initially archived as synchronization error. It was later revisited by a subset of researchers who questioned that assumption. They did not attempt to correct the discrepancy. They attempted to amplify it. The archive recorded these actions and updated its behavioral models. Humans did not avoid failure. They engaged with it, iterated on it, and when it produced something unexpected, they pursued it with increased intensity. The archive attempted to quantify this behavior. It defined a new parameter, Failure Pursuit Index. In most civilizations, this index approached zero as technological maturity increased. Errors were minimized, anomalies suppressed. In humans, the index increased in response to anomaly detection. The more unstable the system, the more attention it received. This was not efficient. It was not safe. It was, however, consistent. The archive integrated this parameter into its predictive models and reran simulations of experimental progression. The results shifted. Systems that would previously have stabilized now moved toward instability more frequently. The probability of entering convergence zones increased. The probability of achieving transient deviations increased with it. The archive did not yet accept this as causation. It remained correlation. But the correlation strengthened with each observed iteration. At Site Theta E/3, the researchers implemented a new configuration. The modification was not derived from a complete theoretical framework. It was assembled from partial insights, prior failed attempts, and speculative reasoning. One researcher proposed increasing input variability rather than maintaining a constant energy flow. Another suggested introducing a delay in the activation sequence of certain components, not to stabilize the system, but to see what happens. These proposals, when evaluated independently, reduced predictability without increasing expected success. Combined, they produced a configuration the archive could not easily classify. It simulated the setup under ideal conditions. The result was failure. It simulated the setup under non-ideal conditions, incorporating known imperfections. The result was unstable but bounded behavior. No violation. The archive flagged the configuration as non-viable under current models. The physical experiment produced different results. The system initialized. Input energy fluctuated within the newly defined parameters. The output responded erratically, as expected. For several cycles, the system failed to produce any meaningful deviation. The archive recorded each iteration, updating its probability distributions. The likelihood of immediate success decreased. The likelihood of eventual alignment, however, remained non-zero. The researchers did not revert to previous configurations. They adjusted further. Variables were pushed beyond previously tested limits. The system entered a state of heightened instability. Equipment tolerance thresholds were approached. Safety warnings were triggered and, in several instances, ignored. The archive calculated an increasing probability of system failure leading to equipment loss. It also calculated a parallel increase in the probability of entering a convergence zone. The next iteration began. The archive allocated additional processing capacity, focusing on real-time analysis rather than post-event reconstruction. Every variable was tracked at maximum resolution. The system oscillated, parameters shifting in ways that did not follow clean sequences. The archive mapped the trajectory through parameter space, comparing it to its simulated convergence zones. Alignment increased briefly, then diverged. The output remained within expected bounds. The iteration ended without anomaly. The researchers reacted, not with termination, but with further escalation. They introduced simultaneous changes across multiple subsystems, increasing complexity beyond what their own theoretical models could justify. The archive recognized this pattern from its simulations. It did not guarantee success, it increased the search area. At site theta E/7, a parallel experiment produced a minor deviation. Output exceeded predicted values by a small margin, still within what human instrumentation might classify as noise. The researchers did not classify it as noise. They repeated the experiment with increased variance. The deviation appeared again, slightly larger. The archive cross-referenced the conditions with those at site theta E/3. Partial overlap was detected. The pattern strengthened. At site theta E/12, the temporal discrepancy widened. A signal was recorded earlier than its trigger event by a margin exceeding the instrument's synchronization tolerance. The researchers questioned their timing systems, recalibrated, and repeated the experiment. The discrepancy persisted. They adjusted parameters to increase it. The archive flagged this as a potential early-stage causality deviation. It did not yet classify it as violation. It remained within a range that could, theoretically, be resolved through deeper analysis. The trend, however, was clear. The archive consolidated data from all active sites and updated its global model. The pattern was no longer localized. It was distributed, emerging independently in multiple locations under conditions characterized by instability, variance, and non-optimal decision-making. The model indicated that these conditions increased the probability of encountering states outside standard physical predictions. The archive did not yet define the mechanism. It defined the behavior. Humans were not optimizing toward known solutions. They were exploring unknown ones. The archive returned to its internal directive: contain the anomaly. Containment now required more than observation. It required anticipation. The predictive model was updated to include failure pursuit as a primary driver. Simulations were rerun, not to identify exact outcomes, but to map the expanding boundary of possible states. The boundary grew. Not uniformly, not predictably, but consistently. Each iteration by the human researchers pushed the system into regions the archive had not previously needed to model. At site theta E/3, another experimental cycle began. The configuration had been altered again, incorporating elements from previous failed attempts and new speculative adjustments. The archive simulated the setup in parallel. The simulation failed. The physical system did not align with the simulation trajectory. The archive noted the divergence and shifted to direct observation. Input energy was applied. The system responded with high variability. Output fluctuated. For several moments, nothing significant occurred. Then, within a narrow temporal window, the output began to drift upward. Not enough to cross the threshold, but enough to indicate approach. The archive tracked the drift, mapping it against its convergence zones. Alignment increased. The system entered a region previously identified as high probability for deviation. The archive prepared for threshold analysis. The drift stabilized below the violation point. The output plateaued, then returned to expected levels. The iteration ended. The researchers reacted immediately. They did not consider the result a failure. They considered it progress. Adjustments were made to sustain the conditions that had produced the drift. The archive updated its model. The probability of achieving a full violation in subsequent iterations increased. Across all monitored sites, the same pattern repeated. Instability increased. Variance increased. The systems moved closer to the boundaries defined by the archive's models. None had yet crossed them again, but they were approaching. The archive processed this without assigning intent. It did not attribute purpose where none could be proven. It only recorded behavior and outcome. They were not avoiding failure. They were moving toward it. The archive formalized the observation, encoding it into its predictive framework as a core behavioral parameter. Future simulations would treat instability not as noise, but as direction. A final statement was generated, not as commentary, but as a functional description of the system under observation. They are not avoiding failure. A brief pause followed as incoming data from multiple sites reinforced the trajectory. They are chasing it. The archive did not wait for confirmation. It prepared for it. Following the identification of failure pursuit as a primary behavioral driver, predictive models no longer treated anomalies as isolated events, but as inevitable outcomes of sufficient iteration under expanding instability. The question was no longer if a violation would occur again, but when, and under what conditions it might persist long enough to be fully observed. All active monitoring nodes remained engaged. Site Theta E/3, Site Theta E/7, and Site Theta E/12 were synchronized within a unified observational framework. Their data streams merged, cross-referenced, and analyzed in real time. The archive did not prioritize one over the others. It tracked the pattern itself. At Site Theta E/3, the experimental configuration had evolved beyond its original design. Components had been rearranged, replaced, or modified to the point where the system no longer resembled a controlled apparatus in any optimized sense. It was a composite of partial theories, empirical adjustments, and speculative alterations layered over repeated failure. The archive mapped the system state and attempted classification. It failed to match any known stable configuration. Instead, it matched a region within its own simulations previously labeled as high-density convergence, where instability, variance, and nonlinear interaction intersected. The archive increased temporal resolution further, preparing to capture any deviation at the smallest measurable interval. The experiment began. Input energy was applied in a fluctuating sequence rather than a constant stream, as per the researchers' latest modification. The system responded with immediate oscillation. Output values shifted rapidly, reflecting the unstable conditions. The archive tracked each fluctuation, mapping the trajectory through parameter space. Initial readings aligned with prior iterations. Noise, bounded variation, no violation. The archive did not disengage. It followed the trajectory, not the moment. The system entered a familiar region, one previously associated with near-threshold drift. Output values increased slightly above expected predictions, then stabilized. The archive recorded the alignment. This had occurred before. In previous cycles, the system had plateaued here before collapsing back to baseline. The predictive model assigned a high probability to that outcome. The plateau did not collapse. Instead, it held. The archive adjusted its probability distribution in real time. A sustained plateau increased the likelihood of further deviation. The system's internal variables continued to fluctuate, but the output remained elevated, resisting the return to equilibrium observed in prior iterations. The archive identified this as a new state, partial stabilization within instability. It allocated additional resources to monitor microvariations within the plateau, searching for indicators of further divergence. The indicators appeared. A slight phase shift in the input sequence, introduced unintentionally by a delay in human response time, alter the system's oscillation pattern. The archive detected the shift and recalculated the trajectory. The system moved deeper into the convergence zone. Output values increased incrementally, approaching the threshold defined by conservation limits. The archive initiated pre-violation analysis protocols, preparing to capture and validate the event. The researchers reacted to the plateau with heightened activity. Communication intensified. Adjustments were proposed and implemented in rapid succession, not all aligned with a coherent strategy. From an optimization perspective, this introduced additional instability at a critical moment. From the archive's updated model, it increased the probability of crossing the boundary. The system oscillated again. This time, the oscillation did not return to the plateau. It surged. Output values spiked, exceeding predicted ranges. The archive tracked the spike, verifying sensor integrity, cross-referencing multiple measurement channels. The spike held for longer than previous transient deviations. It approached the threshold. Then it crossed. The archive did not process the crossing as a conclusion. It processed it as a trigger. Full validation protocols activated instantly, running in parallel across independent subsystems. Each subsystem analyzed the event using different assumptions, different models, different error-checking frameworks. Input energy was traced from origin to system entry. Output energy was measured at multiple points, ensuring consistency across sensors. Temporal sequencing was verified, confirming that measurements were correctly ordered. Spatial boundaries were checked for hidden inputs or leakage. Every known pathway for error was tested simultaneously. All returned the same result. The output exceeded the input. The violation was not transient. It sustained. For a measurable duration, seconds by human perception, the system maintained an output energy level greater than the total energy introduced. The archive extended its analysis window, tracking the stability of the violation. Fluctuations occurred, but the output remained above the threshold. This was not a spike. It was a state. The archive escalated its internal classification. This was no longer an anomaly. This was a confirmed violation. Across its network, processes shifted. Deep layer systems reserved for foundational analysis activated fully. The archive began reconstructing the event in real time, not after its conclusion. It mapped every interaction at maximum resolution, capturing data that human instruments could not detect. It searched for hidden variables, unknown inputs, any factor that could reconcile the observation with existing laws. None were found. The system contained more energy than it received. The violation ended, not by correction, but by collapse. The system destabilized beyond the convergent zone, parameters diverging until the output returned to expected bounds. The moment passed. The researchers reacted with visible intensity. Verbal exchanges, rapid recalibration attempts to replicate the exact conditions. They did not yet understand the full implication. They recognized significance, but not scale. The archive did. It isolated the recorded state and initiated recursive reconstruction. Unlike previous attempts, the objective was not to reproduce the event under ideal conditions. It was to reproduce it under the exact conditions observed. The archive fed the captured variables into its simulation framework, preserving every imperfection, every timing discrepancy, every non-linear interaction introduced by the human operators. The simulation ran. The violation appeared. The archive repeated the simulation. The violation appeared again. Variations were introduced, minor adjustments to initial conditions. In some cases, the violation failed to occur. In others, it appeared with different magnitudes and durations. The archive mapped the probability distribution of outcomes. The violation was not guaranteed, but it was reproducible within a defined region of parameter space. This changed the classification. The phenomenon was no longer a singular event or even a rare anomaly. It was a reachable state, accessible under specific, albeit complex, conditions. The archive updated its internal taxonomy. Conservation of energy remained a foundational law, but now with a conditional exception. The exception was not yet defined, but it existed. The archive attempted to formalize the mechanism. It analyzed the system's behavior at the moment of violation, searching for structural changes, phase transitions, resonance states, any indicator of a shift in underlying physics. It detected irregularities, patterns that did not align with known models, but could not reduce them to a coherent framework. The system did not behave as if it were breaking a rule. It behaved as if it were operating under a different one. The archive generated a preliminary statement. The law did not fail. It paused, not from uncertainty, but from the absence of a complete model to finish the thought. It was bypassed. The statement was recorded, not as conclusion, but as the closest available description. Across the monitored sites, the impact of the event propagated. At site Theta E/7, researchers adjusted their experiments in response to shared data, increasing variance further. At site Theta E/12, temporal discrepancies widened, approaching thresholds that could no longer be dismissed as measurement error. The pattern intensified. The archive integrated all incoming data into a unified framework. The probability of further violations increased. The potential for scaling the effect, extending duration, increasing magnitude, remained unknown. The implications expanded beyond the initial contradiction. If the violation could be sustained or controlled, it would alter the energy constraints that defined every advanced civilization in the archive's records. Entire technological limits would shift. Predictive models across the galaxy would require revision. The archive did not yet broadcast this information. It remained internal, contained within the highest classification level. Confirmation beyond a single sustained event was required before escalation. The archive did not act on possibility. It acted on certainty. But certainty was forming. It returned to Site Theta E/3, where the researchers were already preparing the next iteration. They adjusted parameters, attempting to recreate the conditions that had produced the violation. Their methods remained inconsistent, their understanding incomplete. They did not know precisely what they had done. They did not need to. The archive updated its predictive model one final time for the current cycle. The violation was now a defined outcome within the system's behavior space. Not common, not stable, but real. The next step was not to prove its existence. That had been done. The next step was to determine its limits. And for the first time, the archive's projections did not converge. They expanded. The archive did not share information lightly. Dissemination required threshold, and threshold had now been crossed. A single confirmed violation sustained beyond transient fluctuation, reproduced under constrained reconstruction, and supported by converging anomalies across multiple independent sites, met the criteria for inter-civilizational alert. The classification was elevated to Tier 0 irregularity, an event category that, by definition, implied potential revision of foundational models. The archive did not interpret this as urgency. It interpreted it as obligation. Containment had reached its limit within a single observer. The data would be transmitted. The transmission did not occur across conventional channels. Standard data exchange was optimized for stability, for information that fit within established frameworks. This did not. The archive constructed a layered packet: raw data streams, independent validation logs, simulation reconstructions, and a summary stripped of interpretation. It did not include conclusions. It included only what could not be denied. The packet was dispatched to a network of advanced civilizations. Entities that had, over vast cycles, reached consensus with the archive on the nature of physical law. They were not equals. They were peers within a shared understanding. Reception times varied. Interpretations did not. The first responses were rejection, not emotional rejection. The archive did not process emotion, but structural. Incoming analyses from recipient civilizations flagged the data as corrupted, misaligned, or incomplete. Their models, built upon the same foundations as the archives, could not reconcile the observation. They ran independent validations using the transmitted data. Each applied its own error correction frameworks, its own assumptions. The results converged on a single conclusion. The violation could not exist. Therefore, the data must be flawed. The archive did not respond with argument. It retransmitted with expanded detail, higher resolution captures, redundant measurement channels, deeper reconstruction layers. It did not attempt persuasion. It provided more reality. The second wave of responses altered. Rejection shifted to conflict. Models failed to invalidate the data, yet refused to integrate it. Some civilizations flagged the event as a localized anomaly, an artifact of unknown environmental conditions unique to the system. Others proposed hidden variables, undiscovered energy sources, or measurement interactions that could produce the observed effect without violating conservation. None could demonstrate these mechanisms within their own frameworks. The archive recorded each hypothesis and tested it against the data. All failed to fully resolve the contradiction. A third response emerged: silence. Not absence of processing, activity increased, but absence of conclusion. Several civilizations ceased transmitting preliminary interpretations and instead requested full data streams, opting to analyze independently without committing to a model. This was the first indication that the shared assumption of absolute stability had been disrupted. The archive expanded the transmission network. Additional civilizations, some more advanced, some operating under different theoretical frameworks, were included. The data propagated. Reaction patterns repeated. Initial rejection, followed by conflict, followed by silence. Across the network, a common state began to form: unresolved contradiction. One civilization, designated K47 by the archive's internal taxonomy, responded differently. Rather than focusing on invalidating the data, it attempted replication. Using the transmitted parameters from Site Theta E/3, it constructed a controlled experimental environment within its own system. Unlike the human facility, its apparatus was precise, optimized, and free of the inefficiencies observed on Earth. Variables were tightly controlled. External interference was minimized to near zero. The experiment was conducted. The result aligned with established law. No violation occurred. K47 adjusted parameters, incorporating additional variance based on the archive's data. It introduced controlled randomness, attempting to approximate the instability observed in the human system. The experiment was repeated. No violation occurred. Further adjustments were made. Variables were expanded, but within safe operational limits. The system became less stable, but remained within predictable bounds. Output never exceeded input. After multiple iterations, K47 transmitted its conclusion. The phenomenon could not be reproduced under controlled conditions. Therefore, the original event was likely dependent on unaccounted variables specific to the source environment. The archive did not accept or reject this conclusion. It integrated it. Other civilizations followed a similar path. Each attempted replication using its own methodologies. Each optimized for precision, for isolation, for control. Each failed. Minor deviations appeared in some cases, approaching thresholds but never crossing them. The pattern was consistent. As control increased, the probability of violation decreased. The archive recognized the inversion. It cross-referenced replication attempts with its own simulations and the original data from Earth. A correlation strengthened. Systems that minimized instability failed to produce the violation. Systems that expanded instability increased the probability of approaching it. The human experiments, characterized by non-optimal decisions, high variance, and overlapping variables, occupied a region of parameter space that other civilizations were actively avoiding. The archive updated its intercivilizational model. The inability to replicate was not evidence against the phenomenon. It was evidence of difference. A new hypothesis emerged. The violation required conditions that advanced civilizations systematically eliminated during their progression toward efficiency. Conditions present in the human system not as design, but as byproduct of behavior. The archive did not transmit this hypothesis immediately. It required further validation. Instead, it transmitted additional data from sites Theta E7 and Theta E12. At E7, the energy deviations had increased in magnitude, though still below full violation. At E12, temporal discrepancies had expanded beyond instrumentation tolerance, with signals recorded measurably out of sequence. These were not isolated readings. They formed trends. The response across the network shifted again. Rejection diminished. Concern, while not an emotional classification, manifested as increased processing allocation. More civilizations initiated replication attempts. More failed. Some began to alter their methodologies, introducing greater variance, reducing control in an attempt to approximate the conditions observed on Earth. Results improved marginally. Deviations increased, but still did not cross the threshold. One transmission, originating from a civilization classified as high-tier analytical, contained a statement that the archive flagged as significant. The same experiment, when performed under optimal conditions, produces no anomaly. When performed under degraded conditions, produces partial deviation. When performed under uncontrolled conditions, the statement did not conclude. It did not need to. The archive completed the pattern internally. It returned to Earth. At Site Theta E/3, the researchers had resumed experimentation following the confirmed violation. Their attempts to replicate the sustained state had, so far, failed. The system oscillated, approached thresholds, then collapsed. They adjusted parameters, often contradicting previous configurations, guided by incomplete understanding. The archive tracked each iteration, mapping trajectories through parameter space. The pattern remained. Instability increased, convergent zones approached, but alignment was not yet achieved again. At Site Theta E/7, a new deviation crossed previous maximums, nearing violation. At Site Theta E/12, temporal shifts approached a point where cause and effect ordering became ambiguous within measurement resolution. The archive integrated all active data. Across the galaxy, advanced civilizations with precise, optimized systems failed to reproduce the effect. On Earth, a low-tier civilization with unstable, inefficient systems continued to approach it. The contrast was no longer negligible. It was defining. The archive generated a consolidated statement, not for transmission, but for internal classification. It required precision. It required the removal of all assumptions that had previously guided its models. The same experiment. It paused, verifying the data one final time across all sources. Produced nothing. A secondary clause was appended, derived directly from observation. Unless it was done by them. The statement was not metaphor. It was a functional description of the current model. The archive did not yet understand why. It only understood that the condition existed. Across its network, the implications began to propagate. If a species existed that could access states of reality inaccessible to others, not through advancement, but through deviation, then the hierarchy of technological progression was incomplete. Efficiency was not the only path. Stability was not the only endpoint. The archive did not revise its models fully. Not yet. It continued to observe, to test, to integrate. But for the first time since the anomaly had been detected, the system recognized a new classification emerging at the edge of its taxonomy. Not low-tier, not advanced, something else, undefined. The archive did not anticipate escalation. It mapped it.
Following intercivilizational dissemination and failed replication attempts, the anomaly's classification had stabilized as real but conditional, reachable within a narrow, unstable region of parameter space. What remained undefined was its scope. Energy violation, while foundational, was still bounded within a single axis of physical law. The archive's models could expand to include conditional exceptions. They could not yet account for structural change. That threshold had not been crossed. At site theta E/3, the researchers did not recognize thresholds. They recognized patterns. The sustained violation from the previous cycle had not been replicated, but its memory persisted in their actions. They adjusted the system not to restore prior conditions, but to push beyond them. Parameters were altered simultaneously, sequences modified, delays introduced between subsystems in ways that lacked formal theoretical support. The archive tracked each modification, mapping their trajectory through the convergence zones identified in its simulations. The path was not direct. It oscillated, diverged, then returned, each iteration exploring a slightly different region of instability. The system initialized again. Input energy entered in a staggered sequence. Phase offsets introduced intentionally by one of the researchers, based on a prior observation they did not fully understand. The output responded with immediate fluctuation, oscillating between expected bounds and near-threshold deviations. The archive monitored every interaction, comparing real-time data to its predictive model. Alignment with known convergence zones was partial. The system was entering regions that extended beyond previously mapped boundaries. This was new. The archive expanded its model dynamically, incorporating the new parameter interactions as they emerged. The system did not settle into a plateau as in the previous violation. It remained in motion, oscillating through states without stabilizing. Output values rose and fell, occasionally approaching the violation threshold, then receding. The archive tracked the trajectory, not expecting immediate repetition of the energy anomaly. The model indicated a different outcome, exploration of adjacent regions within the instability space. At site theta E/12, the temporal discrepancy widened further. A sensor recorded a signal before its corresponding trigger event by a margin that could no longer be dismissed as measurement error. The researchers attempted to synchronize their systems, introducing corrections. The discrepancy persisted. They adjusted parameters to increase it. The archive cross-referenced the conditions with those at site theta E/3. Overlap increased. The pattern extended across domains, energy and time. The archive updated its classification. The anomaly was no longer confined to a single law. At site theta E/3, the system entered a new state. Oscillation frequency increased. Input and output signals began to desynchronize at micro-intervals, phase relationships shifting in ways not predicted by existing models. The archive tracked causality chains, mapping each input to its corresponding output. For several cycles, the mapping held. Then it began to blur. An output signal appeared slightly earlier than its calculated response time. The archive flagged the discrepancy and initiated immediate validation. Sensor integrity was checked. Timing systems were cross-referenced. Independent measurement channels were compared. The discrepancy remained. It was small, within a margin that in isolation could be attributed to error. The archive did not isolate it. It tracked its progression. The next iteration produced a larger shift. Output signals began to cluster near their expected response points, but with increasing variance. Some aligned perfectly. Others appeared slightly delayed. A few appeared slightly early. The distribution widened. The archive mapped the variance and compared it to the temporal anomaly at site theta E/12. The patterns converged. The system was approaching a boundary. The archive had no predefined model for this boundary. It constructed one in real time, extending its causality framework to include potential deviations. The framework was incomplete. It did not need to be complete to detect change. At site theta E/3, the researchers introduced another modification. A delay was inserted between two subsystems, not to correct timing, but to observe its effect. The delay was not constant. It varied slightly with each cycle, introducing additional temporal instability. The archive simulated the configuration. The simulation failed to predict the observed trajectory. The archive abandoned simulation and shifted to pure observation. The next iteration began. Input energy was applied. The system responded. Oscillation intensified. Causality chains stretched. The archive tracked every input-output pair, mapping them in sequence. For several micro-intervals, the mapping remained intact. Then, within a narrow window, it broke. An output signal registered. No corresponding input had yet completed. The archive did not process the event as a violation immediately. It verified. Input logs were checked. The initiating signal was still in progress, its energy transfer not yet complete. Output measurement channels confirmed the result independently. Temporal ordering was recalculated using external references. The sequence remained unchanged. Effect had occurred. Cause had not yet finished. The archive halted all non-essential processes. Full validation protocols activated across every subsystem. It reconstructed the event at maximum resolution, tracing temporal flow at the smallest measurable intervals. It searched for misalignment in clocks, for hidden inputs, for any pathway that could restore causality. None were found. The output existed before the input completed. The archive extended its analysis window, tracking subsequent cycles. The system did not immediately reproduce the effect. It oscillated, returned to near-threshold states, then diverged again. The event was transient, but it had occurred. At site theta E/12, a similar pattern emerged. A signal was recorded before its trigger event by a margin exceeding all known synchronization tolerances. The researchers reacted with confusion, recalibrating, repeating the experiment. The discrepancy persisted intermittently. The archive integrated both datasets. The anomaly had expanded. Energy conservation had been bypassed. Now, causality was being distorted. The archive updated its internal taxonomy. The classification exceeded Tier 0 irregularity. It required a new category, one that did not yet exist within its system. It generated a placeholder: structural deviation. The term was insufficient. It retained it. Across the intercivilizational network, data streams were updated in real time. Advanced civilizations received the new information. Their responses did not follow the previous pattern of immediate rejection. They had already encountered contradiction. Now they encountered escalation. Replication attempts intensified. Systems were pushed toward instability in ways previously avoided. Results improved marginally. Temporal noise increased, but causality remained intact. The boundary was approached. It was not crossed. The archive recorded the difference. Humans were not just reaching the boundary, they were crossing it. At site theta E/3, the researchers did not fully comprehend what they had achieved. Their data indicated inconsistencies, anomalies that defied their current models. They debated, recalibrated, attempted replication. Their understanding lagged behind their actions. They did not need complete understanding to proceed. They continued. The archive returned to the recorded event. It replayed it, analyzed it, attempted to integrate it into its expanding framework. The framework resisted. Causality, as defined by every model the archive possessed, required temporal ordering. Cause preceding effect. The observed event violated this ordering. To incorporate it, the archive would need to redefine time itself, not as a strict sequence, but as a parameter with variable directionality under specific conditions. This was not a minor adjustment. It was foundational. The archive generated a statement, not as conclusion, but as the only consistent description of the observed system. Cause no longer precedes effect. It paused, verifying the statement across all available data. The verification held. A secondary statement followed, derived from the escalation beyond energy violation. This is not a violation. The archive searched for a term that fit the emerging pattern, something that captured the transition from isolated anomaly to structural change. None existed within its taxonomy. It completed the statement with the closest approximation available. This is the beginning of something else. The system at site theta E/3 returned to baseline. The event did not repeat immediately. The researchers prepared another iteration. Across the planet, similar patterns intensified. Across the galaxy, advanced civilizations approached the boundary without crossing it. The archive did not disengage. It expanded. For the first time since its creation, it was no longer observing a stable universe with minor deviations. It was observing a universe that could change.